Hi guys, Dr. Orlando here. Just wanted to talk to you about the properties of water. Remember, water is a polar covalent molecule, and that it has a negative end and a positive end, partially negative, partially positive. Okay. It is covalent because the hydrogens and the oxygens are sharing pairs of electrons. Water has some unique properties. We talked about cohesion. Cohesion meaning that the water molecules stick to each other. Okay, think to yourself, why would water molecules stick together? If you have to pause it for a minute to think about it, do that, because I'm going to say the answer here. They stick to each other because of H bonds, hydrogen bonds. Remember the attraction, those weak electrical attractions that attract the hydrogens to the oxygens of separate water molecules. It's what is responsible for surface tension of water. Okay. Then you have adhesion. And adhesion is when water sticks to other stuff. Like in class when I talked about if I threw my pen at the board, it didn't stick to the board, right? But if I threw water at the board, the water would stick. It would eventually drip down or dry off, but some of the water would stick. So again, it is the H bonds of water that are sticking to the surfaces. Okay? So adhesion is also what is responsible for when you're trying to read a graduated cylinder, right? When you're reading a graduated cylinder, it's graduated like that, but your water line kind of takes on this upside down bell-shaped curve. So you have to read it at the bottom of the bell, because on the sides, it looks like it would be much higher if you were to read it there. And that's simply adhesion. Those water molecules are sticking to the side of the graduated cylinder and climbing up it just a little bit. Okay, so that's cohesion and adhesion. Water is obviously vital for life. And a lot of times you'll hear textbooks or people say that water is the universal solvent. And I don't know if universal is the best word for it, but it certainly is a major solvent in our world. So what does that mean? Well, when you take a beaker like this and you put water in it, you would say that the water is the solvent. The little yellow stuff I'm putting in here, we could say this is sodium chloride that we're dripping in here, some table salt. We would say that that is the solute, the stuff we put in, okay? And collectively, we would call this thing a solution, since that solute would dissolve in there, and now we have a cup of salt water. Okay? So with respect to that solute, it can be different things. Okay, let's go on to our next page. With water, if we want to put stuff into water, we find that sometimes things mix and sometimes they don't. And so why is that? Well, if we have something that is hydrophilic versus something that is hydrophobic, you see this. So the hydrophilic means, if you were to translate it literally, water-loving. Hydrophobic, water-fearing. Okay. When in fact, all it really means is whether or not it dissolves in water and distributes evenly. So hydrophilic, we get even distribution. Like for example, if we were to put salt in water, it would dissolve and distribute evenly throughout the beaker. With hydrophobic, it does not distribute. Does not distribute in water. The solute, whatever you're adding to the water, you would say that substance is hydrophobic if it does not distribute. Okay, so what are some examples of hydrophilic substances? Most of our salts, NaCl for example, would distribute evenly in water. We saw that with the ionic bonding, that ionic bonds can be broken by water. Sugar, C6H12O6, it's a simple sugar. We know that if we put sugar in our iced tea that it dissolves. Some other household things maybe. Vinegar distributes evenly. NaOH. NaOH is sodium hydroxide lye cleaning. That also would distribute evenly. NaOH is ionically bonded as well, so if you put that in water, boom, it separates. Hydrophobic examples, think of things that would not dissolve in water easily, so things like oils, fats. Difference between fats and oils is simply how liquid they are. So our oils are liquid at room temperature and fats are solid at room temperature. Typically oils come from plants and fats come from animals, but there are some exceptions there. Okay, and then one that we have drawn, alkenes. I don't think I've used this word with you yet, but an alkene is what we call a saturated hydrocarbon. We have learned the term hydrocarbon. We know that hydrocarbons are made up of carbons and hydrogens. Saturated means that the carbon is surrounded by as many hydrogens as possible. So you've got single bonds connecting the hydrogen. So in this case, this is a saturated hydrocarbon because we can't get any more hydrogens around it if we tried. And you know this hydrocarbon, this is methane. Okay, notice, let's see, we could also put, just make a mention of covalent bonds and which ones would be hydrophilic and which ones would be phobic. So with respect to covalent bonds, we can have nonpolar or polar covalent bonds. Polar covalent bonds are hydrophilic. Nonpolar, like this example here, covalent bonds are going to be hydrophobic. So those go hand in hand. All right, so that's the properties of water. If you have any questions, please feel free to email me or call me.